Okay, good afternoon everyone. Today I am going to discuss about the grid and cloud computing, that is topic 2. So coming to the topic 2, this is the technologies for network based systems. So I am having some contents here. So today in this section I am going to explain about this content, that is multi-core CPUs and multi-threading technologies, GPU computing to exascale and beyond, memory storage and wide area networking, virtual machines and virtualization middleware, data center virtualization for cloud computing. So these are the different topics I am going to explain in this section, that is technologies for network based systems. So coming to the first, that is before going to explain these technologies for multi-core CPUs and multi-threading technologies, first of all we have to study some about technologies for network based systems. So with the concept of this scalable computing, over the scalable computing, it is the time to learn about the hardware, software and network technologies for distributed computing systems design and applications. So what is the technologies for network based systems? So in previous class we have discussed about the concept of scalable computing over the internet. So regarding that topic we are going to learn about the hardware, software and network technologies. So for distributed computing systems, designs and applications. So we will mainly focus on the feasible approaches to build a distributed operating system for handling the massive parallelism in a distributed environment. So this is called the technologies for network based systems. Coming to the multi-core CPUs and multi-threading technologies. So in this multi-core CPU and multi-threading technologies, over the past 30 years, the growth of component and network technologies is increases. So the growth of component and network technologies is increases. They are crucial to the development of HTC and HPC systems. So if you see the figure, we can understand the processor speed is measured in millions of instructions per second, that is MIPS, millions instructions per second, and network band is measured in megabits per second or gigabits per second. So over the past 30 years, the growth of component and network technologies is increases. So they are very crucial in development of the HPC and HTC systems. So this is the diagram of the HPC and HTC system. So this is the diagram. So regarding this diagram, I am going to explain about this processor. That is, the processor speed is, this is the processor speed. So whatever the graphs we are having, this is the curve line. So upper curve line is the processors, different processors we are using. The processor speed is measured in millions of instructions per second, and network bandwidth is measured in megabits per second or gigabits per second. The unit of G. So G means what? G refers to be a 1 gigabits per second Ethernet bandwidth. Okay, na? So this is the micro-core, multi-core CPUs and multi-threading technologies. Now coming to advanced in CPU processors. So today advanced CPUs and microprocessor chips assumes a multi-core architecture with dual, quad, 6 or more processing cores. So these processors learn about parallelism at instruction level parallelism, task level parallelisms, and these instruction level parallelisms is nothing but it measures how many instructions has computer program can be executed at the same time. We having two approaches, that is hardware and software. Hardware level works for dynamic parallelism and software is work for static parallelism. So this is called the instruction level parallelism. So what is mean by processor speed growth? The processor speed growth is arranged in upper curve. The processor speed curve is, so this is the diagram. If you see diagram, we can understand. So in the upper curve, whatever we are seeing here, Intel 286, Motorola 6830 and 68030, Motorola, Intel Pentium 4, Intel Pentium 3. So these are the different types of processor speeds. These are the processors, and this is the increasing. This is the speed, and this is the performance level increasing from one level to the another level. So this is the growth of the processors. The processor speed growth is arranged in upper curve in the figure. In this figure, across generations of microprocessors, or CMPs, chip microprocessor, or CMPs, chip microprocessor. We see the growth from 1 Mbps, 1 micro, we see the growth from 1 millions instructions per second, millions instruction per second for wax 780, 11 per 11 bar 780 in 1978. In 1978 లో మన ప్రాసెసర్ అనేది ఎక్కడి నుంచి స్టార్ట్ అయింది మా wax 780 నుంచి స్టార్ట్ అయింది. సో ఓకేనా, ఇన్ ద 1978 to 1000, 1978, if you see the 1978, so how much ma 1000, 1978 wax 780, 1 millions instructions per second, at to 1800 millions instruction per second for Intel Pentium 4 in 2002. Okay, so up to a 22,000 million instruction per second peak for Sun Niagara 2 in 2008. So in this figure we use the Moore's law, has proven to be pretty accurate in this case. So the clock rate for this processor increased from 10 megahertz for the Intel Pentium 286 to 4 gigahertz for Pentium 4 in 30 years. So it is used for integrating the circuit chips, increasing the microprocessor memory, digital logic circuit transistors. So clock rate reached to its limit on CMOS based chips due to power limitations. At the time of this writing very few CPU chips, at the time of this writing very few CPU chips run with the clock rate 5 gigahertz. In other words, the clock rate will not continue to improve the chips technology. Okay, IPL means what? ILP means what? Instruction level parallelism. The instruction level parallelism highly utilized. The instruction level parallelism is highly utilized in modern CPU processors. So the instruction level parallelism, in the instruction level parallelism, so in the instruction level parallelism, we are utilizing highly modern CPU processors. In the instruction level parallelism mechanism, we include the multiple issues superscalar architecture. What is mean by superscalar architecture? It is a CPU that implements a form of parallelism called ILP within a single processor. So in this ILP, instruction level parallelism mechanism, includes the multi-issue superscalar architecture, dynamic branch prediction, speculation execution. So these are mechanisms we are using in the instruction level parallelism. So I already told superscalar architecture is nothing but it is a CPU that implements a form of parallelism called ILP within a single processor. The ILP techniques depends on the instruction level parallelism. Techniques depends on hardware and compile support. So DLP and task level DLP means data level parallelism and task level parallelism. Data level parallelism contains the multiprocessor parallel computing within a parallel computing, and DLP and TLP highly learn about the graphics processing units, GPUs that contains the many core architecture with hundreds to thousands of simple cores, Okay, so this is the diagram. So this is the diagram. So this is the diagram. So each core is essential processor. Each core is essential processor with its own private cache, L1 cache, and multiple cores are housed in same chip with a L2 cache that is shared by all the cores. This is the diagram. So in this diagram, both multi-core CPUs and many core GPU processors can be handled multiple instruction threads at different magnitudes today. So in this architecture shows the typical multi-core processor. So each core is essentially a processor. With its own private cache, that is L1 cache. Multiple cores are housed in one same chip with an L2 cache. That shared by all the cores. So what is mean by core 1 we having in the multi-core processor we having core 1, core 2, so on, core n. So every core is called as a processor. So every processor we are having its private memory, I mean private cache, that is L1 cache, and these multiple number of processors are housed in one L2 cache that are shared by all the cores, and L2 cache is sharing all the cores, and multiple CMPS could build on multiple CMPS could build the same CPU chip with even L3 cache on chip. Okay, multi-core and multi-threaded CPUs are equipped with many high-ended processors, including the Intel i7 Xeon asynchronous module definitions, Opteron, Sun Niagara, IBM Power 6 Excel processors. So these are the different things we are used in the multi-core and multi-thread CPUs. So Intel i7 means what? It is a family of 64-bit 86 CPUs with 8 cores. Xeon means 400 MHz Platinum microprocessor sharing 100 MHz buses. So this is the each core is multi-threaded. Next coming to multi-core CPU and many core GPU architecture. So multi-core CPU may increases from 10 of cores to hundreds of cores or more in a future. So CPU has reached its limits in terms of learning about massive data level parallelism due to memory wall problems. This has activated the development of many core GPUs with hundreds or more thin cores. Both IA32 and IA34. IA means instruction set architecture. So both IA32 and IA64 instruction set architecture are built into commercial CPUs. Connect to the commercial CPUs. So what is mean by IA32? Intel architecture 32. And IA64 means Intel architecture 64-bit processors. Okay na? So in processor. Now x86 means microprocessor 86. x86 processor have been extended to HPC to HTC systems. So many RISC processors have been replaced with multi-core x86 processors and many core GPU in top 500 systems. So what is mean by many RISC? RISC is nothing but reduced instruction set computer with a small highly set of instructions have been replaced with multi-core x86 processor or many core GPUs in top 500 systems. So in this system we are having the 86 processors. It is developed by Intel based on 8086 microprocessors. So x86 processor is nothing but microprocessor 8086 upgraded and dominated the data centers and supercomputers. So this GPU has been applied. So whatever the GPU means CPU and GPU, we are having two types. GPU is a graphical processing unit. So in this GPU we are having applied the large data center clusters that built with supercomputers in MPPS. MPPS means massively parallel processors. So in the first class we have discussed the image, that is HPC and HTC. In the HPC I am using the MPPS. Instead of that we are using the cluster. So okay na, cluster is nothing but it is cooperatively connected the computers with each other, and that can be share the resources. Okay na, that is called the GPU, and GPU has been applied in large data centers clusters and built with supercomputers in MPPS. So next coming to the multi-threading. So what is mean by multi-threading? Multi-threading technology. So we have 5 independent threads. Of instructions to 4 pipeline data paths. We are having 5 independent threads of instructions to 4 pipeline data paths in each following 5 processors. From left to right, if you see the diagram, so we can see the diagram, we can understand very easily. So this is the diagram of the multi-threading. So in this we are having 5 independent threads. So 1, 2, 1 2 3 4 5. సో ఇది బాక్సెస్ చూస్తున్నారు కదమ్మా. సో దిస్ ఈస్ ద 5 థ్రెడ్స్ వీఆర్ హ్యావింగ్ 5 మల్టీ థ్రెడ్స్. సో ఫర్ ఎవ్రీ 5 ఈచ్ అండ్ ఎవ్రీ multi-threading having the 4 pipeline data paths in each following in every 5 processors, and from left to right 4 issue. First one is a 4 issue superscalar processor, second one is a fine grain multi-thread processor, and third one is a core grain multi-thread processor, fifth one is a dual core processor, fifth one is a simultaneous multi-threaded processor. So coming to the superscalar, what is mean by superscalar processor? Superscalar processor is a single threaded with 4 functional units, each of 3 multi-threaded processor, each having 3 multi-threaded processor is 4-way multi-threaded over 4 functional data paths. సో ఇక్కడ కనిపిస్తుంది కన్నా 4 రెక్టాంగిల్స్ ఉన్నాయి కదా. ఈ 4 రెక్టాంగిల్స్ వచ్చి మనకి 3 వచ్చి షేడెడ్, సేమ్ షేడెడ్ ఉన్నాయి. అందుకని దీన్ని ఏమంటే 4 పార్ట్స్ అనేది 4 వేస్ అనేది సేమ్ షేడెడ్తో ఉన్నాయి. ఓకేనా. ఈచ్ ఆఫ్ ద 3 మల్టీ థ్రెడెడ్, ఈచ్ ఆఫ్ ద. సో ఏమేమి ఉన్నాయి? 4 మల్టీ థ్రెడెడ్ ఏమేమి ఉన్నాయి? 4 సూపర్ స్కేలర్ ప్రాసెసర్ ఒకటి, ఫైన్ మల్టీ థ్రెడ్ ప్రాసెసర్ ఒకటి, అండ్ కోర్స్ మల్టీ థ్రెడెడ్ ప్రాసెసర్. ఈ 3లో త్రీ మల్టీ థ్రెడ్ ప్రాసెసర్స్లో 3 మల్టీ థ్రెడెడ్ వచ్చి 3 మల్టీ థ్రెడెడ్ ప్రాసెసర్లో 3 వచ్చి 4-వే మల్టీ థ్రెడ్ పార్ట్స్, అంటే 4 1 2 3 4 1 2 3 ఇది వచ్చి వేరే వేరేగా ఉన్నాయి. లాస్ట్ 2 అనేది, ముందు 3 అనేది ఏంటంటే సేమ్గా ఉన్నాయి. సేమ్ 4 పార్ట్స్ 4-వే పాత్ అనమాట అది. అందుకని 4 ఫంక్షనల్ డేటా యూనిట్స్ అంటాము. సో ఇందులో సేమ్ షేడెడ్ ఉన్నాయి. ఓకేనా. సో అందుకని 4 ఫంక్షనల్ డేటా యూనిట్ పార్ట్స్ అంటాము. నెక్స్ట్ డ్యూయల్ కోర్ ప్రాసెసర్ వచ్చే 2 ప్రాసెసింగ్ కోర్స్. సో ఇక్కడ డిఫరెంట్గా ఉన్నాయి, ఇక్కడ డిఫరెంట్, మధ్యలో డాటెడ్ లైన్స్ వచ్చాయి. అందుకని డ్యూయల్ కోర్ ప్రాసెసర్స్ అంటాము. దిస్ ఈజ్ ఏ 2 ప్రాసెసింగ్ కోర్స్, ఈచ్ హ్యావింగ్ ఏ సింగిల్ థ్రెడెడ్ 2-వే సూపర్ స్కేలర్ ప్రాసెసర్. Super scalar processor is a CPU that implement a form of parallelism called instruction level parallelism within a single processor. It executes one single instructions per clock cycle. So instructions from different threads are recognized by specific shading patterns for instructions from 5 independent threads. Only instructions from same thread are executed in a superscalar. So superscalar processor చూస్తే సేమ్ షేడెడ్ ఉన్నాయి, అందుకని సేమ్ ఎగ్జిక్యూషన్ అనేది జరుగుతుంది. ఓన్లీ ఇన్స్ట్రక్షన్ ఫ్రమ్ సేమ్ థ్రెడెడ్ ఆర్ ఎగ్జిక్యూటెడ్ ఇన్ ఏ సూపర్ స్కేలర్ ప్రాసెసర్. ఫైన్ గ్రెయిన్ మల్టీ థ్రెడెడ్ స్విచెస్ ఎగ్జిక్యూషన్ చూసుకుంటే, ఇన్స్ట్రక్షన్ చూసుకుంటే డిఫరెంట్ థ్రెడ్స్ ఆఫ్ సైకిల్స్ అనేది ఎగ్జిక్యూట్ అవుతున్నాయి ఇందులో. సో కోర్స్ గ్రెయిన్ మల్టీ థ్రెడింగ్ ఎగ్జిక్యూట్స్ మెనీ. సో ఒక్కొక్క సైకిల్లో ఒక్కొక్క కలర్. ఫస్ట్ 3 వచ్చి ఒక షేడ్, నెక్స్ట్ 4 వచ్చి ఇంకో షేడ్, నెక్స్ట్ 3 వచ్చి ఇంకో షేడ్. అంటే షేడింగ్ ఒక్కొక్క గ్రూప్లో ఒక్కొక్క షేడ్ అనేది చేంజ్ అవుతుంది. అంటే కోర్స్ గ్రెయిన్ మల్టీ థ్రెడింగ్ ఎగ్జిక్యూట్స్ మెనీ ఇన్స్ట్రక్షన్స్ ఫ్రమ్ సేమ్ థ్రెడ్ ఫర్ క్వైట్ ఏ ఫ్యూ సైకిల్. ఒక కొంతసేపు ఒక థ్రెడ్ అనేది ఒక థ్రెడింగ్ అనేది ఎగ్జిక్యూషన్ జరుగుతుంది. ఆఫ్టర్ ఫ్యూ తర్వాత మళ్ళీ కొన్ని. సో అంటే ఒక్కొక్క స్టెప్లో ఒక్కొక్క 4 అలా డిఫరెంట్ షేడింగ్స్లో జరుగుతున్నాయి ఎగ్జిక్యూషన్ అనేది. సో కోర్స్ గ్రెయిన్ మల్టీ థ్రెడింగ్ ఎగ్జిక్యూట్స్ మెనీ ఇన్స్ట్రక్షన్స్ ఫ్రమ్ ద సేమ్ థ్రెడ్ ఫర్ క్వైట్ ఏ ఫ్యూ సైకిల్స్ బిఫోర్ స్విచ్చింగ్ to another thread. The multi-core CMP executes instructions from different threads completely. STM means what? A simultaneous multi-threaded processor, scheduling of instructions from different threads in the same cycle. So the blank squares corresponding to no available instructions for an instruction data path at particular processor cycle. So more blank cells implies lower scheduling efficiency. So in this is the diagram of the multi-threading. Okay na? So next coming to GPU computing to exascale beyond. So GPU exascale. A GPU is a graphic coprocessor or accelerator mounted on a computer graphics card and video card. A GPU offloads the CPU from tedious graphics tasks in video editing applications. The world's first GPU GeForce 256 was marketed by NVIDIA in 1999. This GPU chips can process a minimum of 10 million polygons per second, are used nearly early computers on market today. Okay, market today. So this NVIDIA is called, it is used in computer graphics to compose the images. So polygons why we are using to in the computer we are using in order to compose the images. Some CPU features are integrated into certain CPUs. CPUs are structured with only a few cores, few cores. So in this example, Xeon X560 5670 CPU has 6 cores. So a modern CPU chips can be built, with hundreds of processing cores. So GPUs has utilized massive parallelism by executing many concurrent threads slowly instead of executing a single long thread in a conventional microprocessor very quickly. So this is called the GPU. This is called the GPU computing to exascale and beyond. This is the next one is a how GPUs work. So GPU function as coprocessor attached to a CPU. Coprocessor is computer processor used to supplement the functions of primary processor. It may be floating point, arithmetic graphics, this like. So GPUs are functioned as a coprocessor attached to the CPUs. Today the NVIDIA GPUs has been upgraded to 128 cores on a single chip. So each core on a GPU can handle 8 threads of instructions. This translates having up to 1224 threads executed concurrently on a single GPU. The CPU is optimized. The CPU is optimized for latency checks, latency catches, while GPU is optimized to deliver high throughput with explicit management on chip memory. GPUs are designed to handle a large number of floating point operations in parallel, and GPUs offloads the CPU from all data intensive calculations. So this is called how GPU working of GPU. Next, coming to CPU programming model. So in the there is a interaction between CPU and GPU in performing parallel execution of floating point operations at the same time. So CPU is conventional core processor with limited parallelism. GPU has many core architecture that has hundreds of simple processor cores organized as multiprocessor. So each core has one or more threads. So the CPU instructs the GPU to perform a massive data processing. The bandwidth must be matched between onboard main memory and on-chip GPU memory. So this is the diagram. So this is the diagram of GPU. In this GPU I am having the multiprocessors, and these multiprocessors are grouped in one GPU. So and this is connected with the device memory and main memory. So coming to the main memory, memory storage, wide area networking. So memory storage, wide area networking. In this we are having memory technology. So the capacity results in a wider gap between processors and memory. The upper curve. So this is the diagram of the previous diagram. Regarding the previous diagram we are discussing this. The upper curve plots the growth of the DRAM chip capacity from 16 KB in 1976 to 64 GB in 2011. So this shows the memory chip have experienced a 4 times increases in capacity every 3 times. The memory access time did not improve much in past. So the memory access time did not improve much in past. In fact, the memory wall problems is getting worse as processor gets faster. When the processor gets faster, the memory wall problems will be occurred. Okay, now for hard drives, capacity increased from 260 MB megabits in 1981 to 250 GB in 2004. This presents an appropriately 10 times more increases in capacity every 8 years. The faster the processor, If processor is faster, speed and large memory capacity result in wider okay, wider. This memory walls may become worse, a problem limiting the CPU performance in future. So next coming to disk and storage technology. The rapid growth of flash memory and solid state drivers SDDS also impact the future of HPC and HTC systems, and the lower curve shows the disk storage growth in 7 orders of magnitude in 33 years. The rapid growth of flash memory and solid state drives the future HPC and HTC system. Power increases linearly with respect to clock frequency. The clock rate cannot be increased indefinitely. SSDs are expensive to replace the stable disk arrays. So next coming, this is called the disk storage technology. This is the graph diagram. And next coming to system area interconnects. So a nodes in a small clusters are mostly interconnected by an Ethernet switch or a local area network. A LAN is used to connect a client host to big servers. So a storage area network SAN connects to the network storage such as a disk arrays. So network attached storage connects the client host directly to the disk arrays. All three types of networks appear in large clusters built with commercial network components. If no large distributed storage is stored, a small cluster could be built with a multi-port gigabit Ethernet switch plus copper cables to link and end the machines. So all three networks, this is the diagram. So all the three networks are commercially available. So this is the client host and network storage server. So wide area networking. What is mean by wide area networking? The lower curve plots the rapid growth of Ethernet bandwidth from 10 megabits per second in 1979 to 1 gigabits per second in 1999 to 440 to 100 giga Ethernet in 2011. Okay, it has been speculated that 1 terabits per second network link will become available by 2013. So next one, virtual machines and virtualization middleware. Okay, so virtual machine offers novel solutions to underutilized resources, applications, inflexibility, software manageability, security in existing physical machines. So virtual machines built with virtual resource managed by guest operating system to run specific applications. Between virtual machines and host platform, one needs to deploy the middleware called virtual machine monitor. So this is the virtual machines diagram. So this is the diagram of the virtual machines. In this virtual machine, we are having applications, operating system, okay, and virtual guest applications, hardware and guest applications, virtual machine middleware machines, and these are the different things we are having the virtual machine. Okay, so next come virtual machines. So virtual machine is built with virtual resources managed by the guest operating system to run specific applications. Between the virtual machines and host platform, one needs to deploy the middleware layer called virtual machines monitor VMM, a native VMM installed with a use of VMM called a hypervisor in privileged mode. So next coming to data centers. So data center virtualization for cloud computing. So in this section, the cloud architecture is built with commodity hardware and network devices. The data center designs emphasizes the performance or price ratio over speed performance alone. Okay, and next coming to data center growth. In this data center virtualization for cloud computing, we are having some types: data center growth and cost breakdown. A large data centers may be built with thousands of servers. Smaller data centers are typically built with hundreds of servers. The cost to build and maintain data center servers has increased over the years. So in this 2009 IDC reports the only 30% of data centers, of data center cost goes toward the purchasing IT equipment such as servers and disks. 33% of attributed to chiller and 80% of uninterruptible power supply UPS 9% to computer room air conditioning, and remaining 7% to power distribution, lighting and transformer cost. And above 60% of the cost to run the data centers is allocated to management and maintenance. The server purchase cost did not increase much with time. The cost is electricity and cooling did increases from 5% to 14% in 15 years. So this is called the data center growth and cost breakdown. So low cost design. So high-end switches or routers may be too cost for building data centers. Using high bandwidth networks may not fit economics of cloud computing. So it has a fixed budget. Switches and networks are more desirable in data centers. Similarly, microprocessor 8086 servers is more desired over expensive mainframes. The software layer handles the network traffic, balancing, fault tolerance, expandability. So these are things are occurred in the microprocessor 8086. So next, coming to the convergence of technologies. So cloud computing is having the convergence technologies in 4 areas: hardware virtualization, multi-core chips, utility and grid computing, SOA, Web 2.0, and WS mashups, autonomic computing and data center automation. So these are the different technologies we are using in the data center virtualization and cloud computing. So thank you.